Hey, um, here's um, a little clip from a Futurama episode that introduces some of the ideas that we're going to be looking at when we explore exponential functions and logarithmic functions. I also want to make the point. I know that Futurama is no longer you know, very popular or even well known. It's old, but uh, when you look at Matt Groening uh, productions, the science and the math are almost always correct. Uh, the teams at The Simpsons and at Futurama have always used consultants that get the details right. So when we look at this problem and make our calculations, we'll come up with the number that is presented in the little clip. Just a note, it's possible to get things right. Um, I want to introduce the topic of exponential functions uh, with with a financial application, and just give a sense of where an exponential function arises very naturally in our world. Every single one of us is involved in banks or credit in some way, or will be soon, and the exponential function features centrally in in the financial world. So the one note that ties in with calculus, in as much as this is a pre-calculus class, is what is to observe and note for you to decide how is an exponential function different than a polynomial function. What is the major difference? So that will be important for us here, but very important in calculus. Good to know when dealing with an exponential function. What is this thing? And how do I know that it's an exponential function? So this is compound interest. Compound interest means that money is deposited in a financial institution. The assumption is that the account is left undisturbed by a customer, and that the bank adds interest on the current balance. The current balance at any future time will include the original amount deposited, called the principal, P, with variable name P, fairly uniformly, together with the interest that has accrued. So banks pay or bribe investors to leave money with the bank by giving out a token of the bank's appreciation. The bank's appreciation called interest. If you will keep your money in the bank, here is a little bit of here's a little token of our appreciation. So what I have indicated here is that at the end of the first year, this is compound interest that's compounded yearly. So at the end of the first year, on December 31st, let's say, the amount in the account, the bank balance, will be whatever the principal is plus the interest earned. And the interest is just going to be some fixed percent of the initial amount, in this case, the initial amount deposited. It's a fixed amount of the current balance in general. Here it is a fixed amount of the current of the amount initially deposited. a little bit of factoring. And after 1 year, the amount in the bank is not just the amount that was initially deposited on the 1st of January, but is in fact that amount, the principal, times this number, which is slightly greater than 1 plus the interest rate. At the end of year 2, the balance for that year has been the amount that the bank calculated at the end of year 1 that sat there for a full year. So the bank now here is going to give, hold on, the bank here, right here, is going to give interest based not on the initial amount deposited, but on the amount that has been in the bank for the past year. So it's the bank balance from the previous year plus the interest earned. Again, a little factoring and looks much like the previous step here, much like, oops, ignore that. Oh, much like this step here. But now A1 is itself factored in terms of the initial deposit. And when these two terms are combined, or these two factors are combined, it's 1 plus r quantity squared. So at the end of the first year, it's the principal times the quantity 1 plus r raised to the first power. Remember, here, there is a 1, but it's in white font. We can't see it. Now it's more explicit. Now it's explicit. At the end of the second year, it's explicit. The amount in the bank balance is, let me get a highlighter here, is this, and you will see a pattern quickly emerge. The principal, the amount that was initially deposited, times the quantity 1 plus r raised to the 2. End of the second year, raised to the second power. And I'm going to skip ahead now. End of the third year, third power. Fourth year, the balance at the end of the fourth year is the principal times the quantity 1 plus r raised to the fourth. The balance at the end of the 12th year is the principal times the quantity 1 plus r to the 12th, right? And so in general, what compound interest, where interest is computed annually every year once, the amount in the bank, A, or the bank balance, is the principal, the amount that was initially deposited, times the quantity 1 plus r. A reminder that rates in percents are not numbers. A percent is not a number. It's not, percents are not part of our real number system. Percents are ways that, hold on just 1 second. Well, I smelled something burning and it's beyond. Okay. So I think we were here at the compound interest formula, which is this. There's an initial amount. Here in the banking world, it's called the principal. There is some sort of a base in here, this growth dial, right? Growth factor, or something that's controlling how fast things are growing. And then there's time. How long is this going on, right? Now, that's this formula here. And it looks like here that everything is a variable. But so what I want us all to think about when we finally do see some exponential functions, where's the variable? Where are the constants? P is going to be a constant, R is going to be a constant. The only constant, or the only variable, excuse me, is going to be T. With polynomials, it's the other way around. The exponent is fixed, is a constant, it's 2 or 7 or 13. And then the base is X or T or R, whatever it is, right? But here it's going to be the other way around. Now, a little bit more detail. Compound interest is more complicated than the story that we started with, where you get interest once a year. If you get it more often than once a year, this n is the number of the frequency of compounding. So you might get interest quarterly or semi-annually or daily, whatever it is. T is going to not be any different. P is not going to be any different. R is not going to be any different. R is the yearly interest rate. What NT now represents is how many times you get interest. Right? So if it's quarterly and it's 1 year has elapsed and you've got interest 4 times. So really, I want to set that up and show an example here. Okay, show an example here and just see how these things plug in. We have $100 deposited, 5% annually. By the way, there is no such thing as a 5% account for you currently, at least in a bank, not available to just mere mortals. The first one is annually. So you put all those numbers in, you put in $100, you have 0.05, n is 1, so it's divided by a white font 1, and we're going to look at 1 year. After 1 year, you have $105, and here you have all the notations here. Semi-annually means every half a year you get interest, so you don't get all of the 0.5% both times. You get half of it each time, and 2 times 1 is 2. And so you get 6 extra cents. So the idea is when it's compounded more often, you get a little more. If it's compounded quarterly 4 times a year, you end up with 9 extra cents. And but however, you may be seeing that there is a slowing down. The jump is not that great. If you go from monthly to daily, you're only going to get an extra and an extra penny. So the next piece is what happens if you go from daily to hourly to minutely to secondly to tenth of a second to nanoseconds to nonstop. That's called continuous compounding. Then there's a different formula. It's beyond the scope of this class really to develop this, but there's the principle, there's the bank balance, there's a number E, it's 2.71828, it's a constant, it's a fixed, very important constant like pi, it's called E, it's Euler's number, Leonhard Euler, E-U-L-E-R, and R is, as before, is the yearly interest rate, and T is the number of years. So we'll get into that, not just to point out, there's that. I wanted to show a couple of questions that we are going to look at, applications of exponential and logarithmic functions. I'm at 13 minutes. I want to wrap up. This is Newton's law of cooling. The question is, you take something out of a hot environment, you put it in at room temperature or in a cooling bath. How is it cooling? Exponential functions. Here's a fun little problem for you to think about, and I'm going to actually stop the recording here. The PowerPoint will be on Canvas and you can look at it. But think about this. You take a piece of a regular sheet of paper, you tear it in half, and you have now a stack. You tear it in half once, you have a stack of two papers. You take that stack, tear it in half. That's the second time you've torn in half. You now have 4 sheets. If you take that stack and tear it the third time, you now have 8 sheets, or 2 to the third. So there's an exponential function there. The question is this: what do you think? Look at the answer on Canvas. After doing that 30 times, how tall is the stack? 40 times, how tall is the stack? 50 times, how tall is the stack? What do you think? All right. I will see you when things are better.